I saw Alan.
Good morning, everybody, and thank you for joining us for this month's edition of our Bic Gardner online web seminar. Today's topic is color systems for solid and effect colors. Now there are two options available for joining our audio. You can either join via your computer, or you can call in to us by following the directions here on the right. Hopefully everybody has managed to join the audio and is now hearing my voice. If not, I will leave this up for just a few seconds so anyone who has not managed to join us yet can do so.
I'm happy that's a flex. Real.
Okay, moving on. Your speaker today is this guy, myself. My name is Corey Cohen, application specialist with Bic Gardner USA since February 2011, and I specialize in customer education and technical training. Just a few general items before we begin. I have initiated the mute setting for all of our attendees today. So I should be the only person that you hear. I am experiencing some technical difficulties today with this WebEx platform. I'm not sure what's going on, but if for some reason you find that you're not muted, please go ahead and mute yourself. Please document any questions you may have in the chat function. We will have some time at the end of the presentation for a brief question and answer session. So if there are any questions I have not answered by the end of the web seminar, or if you'd like some clarification on any of the slides or the concepts we're about to go over, please just enter that in the chat function, and I will get to as many as I can once the presentation is complete. And yes, you will all be sent a copy of this presentation in PDF format via email once today's presentation is done. So without further ado, let's get to our discussion of color systems for solid and effect colors. And our agenda today is going to include the CLAB color space, CIE-LAB. CIE is, of course, the organization, the International Commission on Illumination, that came up with a lot of these color spaces and equations that have to do with color. So they came up with the LAB color space, and today we'll be discussing the color components LAB and LCH, as well as the color differences, the delta LAB and the delta LCH, as well as the total color difference, delta E. And then we'll get into a discussion of the limitations of the CLAB system and tolerancing in that system. After that, we're going to move on to our weighted color difference methods for solid colors, beginning with a discussion of the general principle, and then getting into some specifics on the delta E2000 equation for solid colors. And finally, we're going to get into weighted color difference methods for metallic and effect colors. Again, we'll discuss the general principle behind these improved color difference equations, as well as a somewhat in-depth discussion of the delta E DIN 6175 part 2 equation for metallic colors. So, starting off with our CLAB color space. This is our LAB color space. It's a three-dimensional space, a three-dimensional coordinate system that contains all available colors, all possible colors, which can be described using these three values: an L value, which is for lightness, an A value, which is for red-green, and a B value, which is for blue-yellow. So for the L axis, the higher the L value, the lighter the color. For the A value, a positive A value indicates the presence of red. The negative A value indicates the presence of green. Similarly, for the blue axis, a positive B value would indicate yellow in the color, and a negative B value will indicate blue. So hopefully everyone is at least somewhat familiar with the C-Lab system and has worked with color measurements before. And so in addition to describing colors in this LAB space using those LAB numbers, you can also describe colors using LCH. So you can use, these are just two different coordinate systems for describing the same colors in the same color space. The LAB, we would call that a Cartesian or a rectangular coordinate system, whereas LCH is more of a polar coordinate system. And so the way that works, the L value is exactly the same. The L axis is the same. The higher the L value, the higher the lightness of the color. But now instead of getting an A and a B value, we're giving a C value, which stands for chroma, which in a few words is basically how much color there is, how colorful it is, or you can say the saturation of the color, how saturated it is. So for example, like a scarlet red, or like a navy blue, we would call that a very chromatic color. It would have a very high C value, whereas a near neutral color like a gray or a beige would have very low chroma, very low C value. So we have L, we have C, and then H gives us the hue angle, and that describes the actual color that you're dealing with: red, yellow, green, whatever. And so the way that works is the positive A axis has a hue angle of 0, so that red axis is a hue angle of 0 degrees. As you go counterclockwise from there on the AB plane, the hue angle increases. So the positive B axis is 90 degrees, the negative A axis is 180 degrees, the negative B axis is 270 degrees. So you describe the hue of the color by an angle on this circle, on this color wheel. So when it comes to C-Lab color space, we like to use different methods depending on whether we're dealing with chromatic or non-chromatic colors, also called achromatic colors. So a non-chromatic color would be one we would consider non-chromatics to be in anything with any color with a C value less than 10. So if the chroma of the color is less than 10, we would call that a non-chromatic color. And we would recommend using LAB coordinates. And then for chromatic colors, which we consider to be any color with a chroma value greater than 10, we would say switch to LCH coordinates. And there's a very good reason for that, which we will get into shortly. So here we have a color in LAB space. And of course, we can describe that color using our L, A, and B values. So here the L value is 62.51, so kind of a medium lightness. The A value is positive 3.31, so we know that there's some red in this color, but that A value is fairly small, so not a whole lot of it. And then the B value is 2.23, and so since it's a positive B value, we know that there's some yellow in this color. But again, that B value is fairly small. I'm not going to give it too much chroma. And so what we end up with is this near neutral sort of dark beige kind of color. And since this is a near neutral color, since this is a non-chromatic color where the chroma value will certainly be less than 10, we would recommend using LAB coordinates for this. And so when we're dealing with LAB coordinates, when we measure a sample, generally we're not too concerned with what are the absolute values of that sample. Usually what we want to know is what is the difference between that sample and a standard. So generally you're going to have a target color that you're aiming for, and we call that the standard. and then you want to know how far your sample is from that target. So to do that, you would measure the LAB values of your standard, you would measure the LAB values of your sample, and then take the difference between them. And so those differences can tell us things about the difference between those two colors. For example, if the delta L value is positive, that means that the sample is lighter than the standard. If it's negative, that means it's darker than the standard. The delta A value can tell us whether the sample is redder or greener than the standard, and the delta B value can tell us whether the sample is yellower or bluer than the standard. But what we really want, ideally, we want to have one value, one number that just tells us what the overall difference is between these two colors, and that is the delta E value. And so here at the bottom right, we have the equation for the delta E star color difference. This is the overall color difference between this sample and standard, and the way we calculate that is by taking the difference in the L values and squaring it, the difference in the A values and square it, and the difference in the B values and square it, add them all together, and then take the square root of that. And so what this actually is this is just the distance formula in this, this color space. So if you were to actually plot your sample and standard in this three-dimensional space and then measure the distance between them, that's actually what you're calculating with this delta E star value. So that overall color difference is just the distance between these 2 points in color space. So now we have a what looks like a chromatic color, this orange color, which we're plotting in LAB space. And now, so this color is, it has an L value of about 58. So again, kind of a medium lightness. We see the chroma here is 47, so that's a fairly high chroma value. Remember, the limit for determining what's chromatic and non-chromatic is 10, and this is, of course, well above a chroma value of 10, and so we would consider this a very chromatic color, which is, of course, why we're now using LCH coordinates rather than LAB. And the hue angle is 38 degrees. So recall that the red axis, the positive A axis, is 0 degrees. The positive B axis, the yellow axis, is 90 degrees. So 38 degrees is going to be somewhere between that red axis and that yellow axis, and so that's going to give us an orange color. Now, when we want to take the component color differences when we're using LCH coordinates, it's a little bit different than LAB. So the way you would calculate the difference in the chroma value, so you have the C value for your sample on the left, and then a little below that you have the C value for your standard. And so the difference in those C values, you can think of it like if you made a circle out of both those values. If you made a circle with the C value of each one as the radius. So you make a circle with the C value of the standard as the radius, and a circle with the C value of the sample as the radius, and the difference in C values would be the difference between those radii. And then to calculate the hue angle, you would, of course, take the angular distance between those two line segments pointing to the standard and sample. And that can be calculated using this equation here. Just some simple algebra and trigonometry. Okay, so now we're going to talk about tolerancing. So beginning with achromatic colors, remember this is what we would typically use LAB coordinates for. So what was done here is that you have a standard, a target color, which is indicated here by this double triangle symbol. And so a bunch of production parts were taken and evaluated visually and sorted into visually acceptable and visually unacceptable based on how close it is to the standard. So we can see in this A-B plot, all these colors were plotted in this graph, and the acceptable colors were plotted as these sort of grayish circles, and the unacceptable colors, the products that were unacceptable visually, were plotted as these red circles with the X in the middle of it. So if we draw a shape around our visually acceptable samples, what we end up with is more or less a circle. And so if we tried to apply A-B tolerances to this, so we're saying on the A-axis, minus this amount. On the B-axis, you can go plus this amount or minus this amount from the standard. What you end up with that is a box. So that's called box tolerancing, because when you apply tolerances to the A and B values, you end up with a box like we see here. And this works pretty well because we can see that that box approximates that circle shape of the visual tolerance shape fairly well. So this is why we like to use LAB tolerances for achromatic colors, for non-chromatic colors, because the box tolerancing does work pretty well when working with non-chromatic colors. But so here we're switching to a chromatic color now. And so we have the same thing. We have a standard in the middle there indicated by that double triangle. And then we have a bunch of production samples which were sorted visually into visually acceptable and visually unacceptable and plotted here again. So now though, if we draw a tolerance shape around our acceptable samples, what we end up with is this elliptical shape. So it's no longer just a circle. It's sort of been stretched out into this ellipse. And so now if we try to apply our A-B tolerances to this, what we get is a box that looks like this. All right, so we've made our A-B tolerances large enough that it encompasses all of the acceptable samples, which is good. That's what we want. But it's now also encompassing a lot of these visually unacceptable samples. So this type of tolerancing is not ideal for a chromatic color like this, because now you're going to be shipping lots of product that may not look so good. So what can we do? Well, one solution, of course, is to just decrease the tolerances. We can lower the A-B tolerances so that we're no longer accepting these visually unacceptable samples. Except now we're also rejecting a lot of the visually acceptable samples. And that's not great either, because now you're going to be tossing out a lot of product that actually looks pretty good. And that's going to be a money waster as well. So this isn't ideal for chromatic colors, this A-B tolerancing. And this is why we typically would switch to LCH tolerancing. So we have our elliptical tolerance shape, and now we're going to have our chroma line and our hue line. And if we now tolerance based on the chroma values and the hue values, what we end up with is this sort of pie slice shape. And it's oriented towards the center of the color space, just like this ellipse is. And so this shape fits the ellipse fairly well. And this is why we recommend using LCH tolerancing for chromatic colors that typically have this elliptical tolerance shape, rather than non-chromatic colors, which have that more circular tolerance shape and can use box tolerances. So here we have sort of an extension of that idea. Here we have a slice of color space. We have an A-B plane in color space. And the idea here is that any two colors within any one of these shapes will be indistinguishable from each other. So in the center of each of these shapes, you can see a little dot, and you can consider that the standard. And so the idea is that any other color within that same shape would be visually indistinguishable from that standard. So these are tolerance shapes for different colors throughout color space. And what you might notice about this is that these tolerance shapes change pretty drastically depending on where we are in color space. So towards the center of color space, where we get to those non-chromatic colors, those color shapes tend to resemble more of a circular shape, as we saw with that previous example. And as you get further, as the chroma values get larger, you get closer to the edge of this circle where you're dealing with very chromatic colors. Those tolerance shapes stretch out and become longer and more elliptical. But even in addition to that, if you look at different colors on this color wheel, if you change the hue angle, you can see that these tolerance shapes are also changing in size and shape. In some regions, they're a lot fatter. In some regions, they're much skinnier. So this sort of serves to illustrate the non-uniformity of C-Lab color space. And then here we have another view of sort of a 3D view of a similar thing where it's showing you different tolerance shapes depending on where you are in color space. So acceptable color differences for lighter shade colors tend to be larger than for darker shades. So you can see as you go up on that L axis, those shapes become larger in general and larger in the L direction. More chromatic colors tend to have larger tolerances than pastels or neutrals. So again, as the chroma value increases, as you get closer to the outside of this color wheel, those tolerance shapes are going to get larger. And so this is why we want weighted color difference methods or improved color difference methods. Because of that non-uniformity in C-Lab space, that non-uniformity sort of requires us to have a different tolerance for every color. Because a delta E that's acceptable for one color may not be acceptable for a different color due to those differences. So that's why we want improved color difference equations. So we have, for solid colors, we have delta E CMC, which was created by the Color Measurement Committee of the Society of Dyers and Colorists. So these are people working with textile samples, and that's what this equation was based on, a visual evaluation of high chroma textile samples. So mostly, we're talking like fabrics, so mostly matte samples, low gloss samples. Then after that came Delta E94, which was published in 1995. That was based on a visual evaluation of RIT sample sets using high gloss, high chromatic solid colors. RIT, by the way, is the Rochester Institute of Technology. They have a PhD program in color, actually, which is pretty cool. And then after that came the Delta E 2000 equation, which was published in 2001. And that's based on visual evaluation of additional sample sets from international institutes such as BAM. So here we're just sort of looking at the general principle behind these improved color difference equations. And the principle is, if you remember that delta E star equation, where you square each component difference, add them together, and then take the square root. So we're retaining that sort of general format for the color difference equation, but we're also applying a scale factor. So now each delta value has a scale factor attached to it. And the idea here is to scale these numbers such that a delta of less than 1 would be within tolerance, and a delta of greater than 1 would be out of tolerance. So now we're going to look a little more in depth into the delta E 2000 color difference equation. So this is based on several already existing data sets, currently published in the following CIE recommendation, very official. It's based on elliptical spacing and LCH. And there are 5 corrections to the C-Lab system. There are corrections for lightness, chroma, and hue, depending on our perception of them. There's a factor for rescaling the A-axis, which improves performance for gray colors. And there's a rotation function which improves performance for blue colors. So here's what that equation looks like. So here at the top, so we essentially have two terms or two sets of terms here. These on the left here, the delta L, delta C, delta H, those are the sort of main terms of the color equation, and we can see that they're each divided by an S value, SL, SC, SH. Those are our scaling factors. And those scaling factors are dependent on the position of the standard in color space. So the equation is actually automatically modifying the outcome. It's modifying that scaling factor, which is going to modify the delta E calculation according to what color you're actually dealing with, where you are in color space. And then you also have these K factors, KL, KC, KH, which are user selectable factors that have to do with things like differences of lighting conditions and things like that. So we have the delta L divided by the scaling factor, the delta C divided by the scaling factor, and the delta H divided by its scaling factor. So those are the first three improvements to C-Lab. And then over to the right there, that term that begins with RT, that is the rotation function, which we'll get into in a little bit. So the fourth modification is again to the A-axis. So here you can see we're calculating primed color components. So we have L prime, A prime, and B prime, where L prime is just equal to L star and B prime is equal to B star. Just the star just indicates the normal CIE LAB coordinates. So really the only modification going on here is with the A number, and that is modified by this G factor, which has to do with how much chroma there is in standard. And so what this does is this sort of serves to stretch out that A-axis in that near neutral range. But as the chroma values get very large, that whole G term sort of goes to zero. So this modification is only for very small values of A. For very low chroma samples, it doesn't really affect anything in the higher chroma range. And then the fifth modification we have is the rotation function. And this is specifically for blue colors in the region with a hue angle of between about 250 and 300 degrees. And so what this does, it serves to tilt that calculated tolerance shape that we're using. So if you remember back to the that color wheel that had all those tolerance shapes in it, they were all different sizes and shapes. They were more circular towards the center and more elliptical towards the outside. Some were fatter, some were skinnier. You have all these differences, but there was one thing that all those tolerance shapes had in common, and that was that the long axis of each of those ellipses was always pointed right towards the center. And what we've come to discover is that visually this actually doesn't match up for blue colors. It's found that the tolerance shape for blue colors is not oriented directly towards the center. They're actually tilted a bit, and that's what this rotation function in this equation accounts for. And so here we have an example of some colors plotted in LAB space, calculated under, with differences calculated under delta E94 on the left and delta E2000 on the right. And you can see the tolerance shape for each in red there. And so on the left, if you look at these samples, most of them appear inside that tolerance shape. So we would say, based on this equation, that most of these samples are within tolerance. But then we switch over to the delta E2000, which has that rotation function. Of course, we're dealing with blue colors here. The rotation function only affects blue colors. But so now that tolerance shape is rotated a little bit. And so we have those same samples against this different tolerance shape under delta E2000. And we see not all of them match so well when we apply this rotation function. The delta E94 is fairly similar to the delta E2000, but it does not have this rotation function. So the 2000 equation is going to give us a bit more accurate picture of whether these samples are actually intolerant or not. So we've talked about weighted color difference methods for solid colors, Delta E CMC, 94, and 2000. These are optimized for solid high chroma colors. And then we have the Delta E DIN 6175 Part 2, which was developed specifically for effect pigments, specifically for metallics, in fact. And these are based on samples of metallic paints with metallic flake in them. And so the DIN 6175 Part 2, that's sort of the, you can think of it as like the umbrella name for this equation, but there are lots of different iterations of it. Delta E BMW has its own equation that's set in a certain way. Delta E GM, Delta E Kia, each automaker likes to have its own equation named after them, but they're all just slight variations of this DIN 617 Part 2 equation. And so while the Delta E CMC 94 and 2000 are really only for solid colors, the DIN 6175 Part 2 is really only for gonio apparent colors, which basically just means colors that are going to change depending on the observation angle, such as metallic paint jobs. But then we also have the Delta E Audi 2000, which takes into account some things from the DIN 6175 equation, as well as the Delta E 2000 equation. And that gives us the Delta E combined value, which sort of takes into account the best of both worlds, the best from the solid equation and the DIN equation. And so the Delta E Audi 2000 is applicable for both solid and effect colors. All right, so getting into the equations for the multi-angle, for the color difference methods for effect colors. So now again, we split them into achromatic or chromatic colors, where achromatic we like to use delta LAB tolerances. For chromatic colors, we like to use delta LCH. Of course, there's going to be a scaling factor to account for the standard's position in color space to make it more uniform. But also, in this case, when we're dealing with effect colors that are going to be measured at multiple angles, the angle actually comes into account as well. That little Greek symbol inside the parentheses you're seeing, that's a gamma symbol, and it's basically a stand-in for the angle of measurement. And so again, just as with the solid color equations, the goal of this equation is, of course, to make it so that if any delta value is less than 1, that would be within tolerance, and when any delta value is greater than 1, that would be out of tolerance. So here we have the actual equation for achromatic and chromatic colors. Of course, very similar. Again, you have the delta LAB or the delta LCH, each with its own scaling factor, that S factor you see in the denominator, and of course that's going to be dependent on the position of the standard in color space. But what we also have are these G factors, and these G factors are called application factors, or application parameters. So the idea here is that depending on the application, your tolerances might need to be tighter or they might need to be a little looser. For example, typically the tolerances for QCing an incoming batch of paint will be tighter than the tolerances for measuring your parts off of the production line. So that G factor can be changed to account for that. And now here we have the delta E Audi 2000 equation. and we can see the scaling factors for the L, C, and H values. And each of these is going to contain both a flop term and a chroma term. So the chroma term, we've seen something like this before, where it just adjusts the calculation based on the position of the standard in color space. But that flop term, that's telling us how much color flop or light dark flop there is in the material. So real quick, light dark flop is just when the apparent lightness of your surface changes with viewing angle, and color flop is where the apparent chroma or hue of the surface changes depending on viewing angle. And so there's a term in this delta E Audi 2000 equation for the flop that takes the flop into account, because that does affect how we see or how we're able to differentiate different colors when we're looking at them. So as an example, here we have a car. The side of this car body, and in fact the side of most car bodies, are not perfectly flat. They're going to have lots of curves. And so if the surface has a strong light-dark flop, a lot of different shades are going to appear. You're going to see a lot of different lightnesses. And so visual perception is much more tolerant to lightness deviations of add-on parts for colors with high light-dark flop compared to solid colors with the same lightness all over the car body. So what this is saying is that when you're dealing with a car or a part that already has a lot of light-dark flop, you're going to be seeing lots of different lightnesses anyway, just from the curvature and just from slight changes in the viewing angle. And so if the add-on part, if you're looking at two parts next to each other that maybe don't match perfectly in the lightness value, the equation, well, your eye is going to be a bit more forgiving of that if there's already a lot of light-dark flop. And so the equation is also going to be more forgiving when calculating that delta E value, because it's harder for us to visually tell the difference between two colors when there's already a lot of light-dark flop going on, a lot of sort of chaos going on in our eyes. And so here we have another car with a strong color flop effect. So now we're not just seeing differences in lightness, we're seeing actual differences in hue and chroma. And so the question is, are the different color shades caused by different observation angles or by a real color formulation difference? And again, it's harder for us to tell. So visual evaluation will accept larger chromatic and hue deviation of add-on parts compared to a similar solid color. Similarly to the last slide, if we're dealing with a surface that already has a lot of color flop, we're already seeing a lot of different hues, it's going to be more difficult for our eye to tell the difference between the difference in color between two different panels. So again, when there's a lot of color flop in the surface, our eyes are going to be more forgiving of slight color differences, and so the equation will be more forgiving of slight color differences as well. And that's why the flop terms are built into this delta E Audi 2000 equation. So here we have a correlation study of how well each of these equations matches up with what we see visually. And so here, if the R squared value, the lower the R squared value is, the worse the correlation is. The closer the R squared value is to 1, the better the correlation is between the two, between the visual and the calculated method. So we can see that for the delta E star and delta E94 equations, when we're dealing with this white solid color, the correlation is pretty good. But when we go to this white pearl color that has effect pigments in it, that's going to exhibit some flop effects, these two equations aren't so good for that. And so you see that the R squared values are 0.1 and 0.3, so not very good correlation. When we go to the improved difference equations for the, specifically for effect colors, the DIN, the ALDI, the delta E combined, we can see that those R squared values are much higher for that white pearl. And so these equations are much more suited to effect colors than the delta E star and delta E 94. So here, just sort of as an overview for solid colors, we can use the delta E star value. We can, of course, use the component color differences, DL, DA, DB. We can use an improved color difference equation like delta E 94 or 2000. And those are, of course, only for solid colors. And then for metallics, we have the DIN 6175-2 equation, which is specifically for metallic colors, for effect pigments, and doesn't always work so well for solid colors. But then those two concepts are combined in the delta E ALDI 2000, which is based both on the DIN 6175 part 2 and some concepts from the delta E 2000 equation to give us the delta E combined, which can be used for both solid and effect colors. And then here we have a bunch of automakers that are currently using improved color difference equations. Many of these we work with directly. We've worked with, GM has come up with the delta E GM, the difference method just for them. Same with FCA, same with Kia, same with BMW. So we work closely with various automakers to get them exactly what they want to see in our software. And here we have two of our instruments for color measurement. Over on the left, we have our single angle color instrument, the Spectra 2 guide. And this comes in both a 45-0 and a D8 version, with the D8 version capable of doing both spin and specs measurements. And in that meter, the Spectra 2 guide also has a built-in fluorimeter for accurate fluorescence measurement, as well as a built-in 60-degree gloss meter. And then over to the right, we have our BIC-MAC I instrument. MAC stands for multi-angle color. That's why it's the BIC-MAC I. And that is our multi-angle spectrophotometer for effect colors. So it measures at 6 different measurement angles, as well as doing characterization of the effect pigments, giving you a sparkle and a graininess value. And then we also have the Smart Chart software, which comes with both of these instruments, which makes it very easy to communicate values across supply chains, across different plants and customers and suppliers and all that. Okay, so that pretty much does it for the presentation today. We just want to let you know that you don't have to wait for a web seminar to have your questions answered. You're seeing here the Bic Gardner Technical Service Team, including those of us here in the US, as well as our colleagues over at our headquarters in Geretsried, Germany. And here you will also see all of our contact info. We do encourage you to contact us directly. We'd love to discuss your application with you and answer questions for you at any time. So just a few cleanup tasks. Our next monthly Bic Gardner web seminar will be on effect colors, and that will be in early December. Look for it in a couple weeks. When we are able to travel, we do like to perform on-site seminars for our customers. So when this whole pandemic ends, if you have a desire for us to come to you, we can bring all of our instruments for you to touch and handle and see how they work. And we can also customize a presentation specifically for your needs. We do have a new website. Check us out at byk-instruments.com. And we do have a number of videos that show you how our instruments work. You can reach those at youtube.com/ www.fluorescence.com/user/BIC-video. And of course, once the travel restrictions are lifted, we would love to host you at one of our locations, either our North American headquarters here in Columbia, Maryland, or our global headquarters in Geretsried, Germany, which you can see over at the top left. That is where much of our R&D and production goes on. So I know my colleagues over in Germany would love to host anyone who would care to visit. They can show you around the building, show you our production. It's settled right near the Alps, so there's plenty of beautiful countryside to see there. And also, German beer is delicious. I've tested this thoroughly, and I can confirm that that is so. Okay, and that does it for the presentation. We will now move on to our question and answer session. If you have any questions you'd like answered, again, please document them in the chat function. So someone asked, what is the Delta E CMC 1-to-1 or 2-to-1 good for based on your presentation? Should it be replaced by Delta E 2000 or Delta E 94, generally speaking? So first of all, those ratios, the 1-to-1 or the 2-to-1, these are factors, L and C factors that you can apply to the Delta E CMC equation that actually adjusts that tolerance shape. It can stretch it out in the L direction or make it shorter and fatter and to sort of suit your specific needs. But I think the main question is when to use Delta E CMC and when to use 94 or 2000. So really you want to base that on what kind of product you're dealing with. Remember that Delta E CMC, that was created by a textiles group, and so the samples they used were all high chroma, low gloss textile samples. So if you're dealing with low gloss samples, you might consider using Delta E CMC. The 94 and 2000 equations were based on glossy solid colored paint. And so if you're dealing with glossier paint or plastic, you might consider using the 94 or the 2000 equation. Any plans for special effects color matching software? We do have a color matching software for effect pigments that does take multiple measurements from multiple angles into account. So yes, we do have something for that. I encourage you to contact us directly if you'd like to discuss that. Yes, this will be available to watch later. This has been recorded. It's still being recorded. If you go to our website, to the web page where you initially registered for this web seminar, you can access the recording there for, I believe, the next month. Is there an application where YXY will be better than LAB? So there is a metric that's commonly referred to as the light reflectance value or the overall reflectance of the surface. And that is actually the capital Y value in the YXY. So it's useful for that, and usually would be measured with a sphere spin instrument. Other than that, I'd say in most cases, LAD is going to be superior, or at least more intuitive. Again, yes, we will be sending out this presentation to everybody via email in a PDF version. What information do I miss if I use Delta 2000 for a silver metallic color? So the Delta E2000 doesn't take into account differences due to the measurement angle. So there are certain measurement angles, what we call the near specular angles, the 15 and negative 15 degree angles, which tend to get much more reflectance than at the off specular angles, like the 75 and the 110. And so that is sort of wrapped up into the equation to get better tolerancing at all angles. And so that's what you're sort of missing if you use Delta E2000 rather than the DIN equation. Do you have plotting software where you can input two sets of LEDs to compare color and see it visually? We do have software that can graph colors that you can then see in the relative positions in color space. You cannot achieve that by simply inputting the LED values. They do need to be actual measurements, which include the reflectance data and everything. So you can't just input LED values. They do need to be downloaded measurements from one of our instruments. Sounds like these newer systems are all based on CLAB or CIE-LCH, and the corrections are all for calculating a delta E from a standard. For the most part, that's correct. Most of these equations, or at least I should say some of these equations, don't modify the actual L, A, and B values. It's only those improvements. The scaling is only going to come out in the delta E value. But some equations do use modified LAB values, and those are where we see the primed values, L prime, A prime, B prime. I went over that one example in the delta E2000 equation where it actually modifies the A value, makes it an A prime value. So yes, there are some equations that do modify the LAB or LCH values directly. Just look for that prime symbol, that sort of apostrophe symbol rather than the star. I have mainly dark non-chromatic colors. Should I keep using Delta E CMC or should I use 94 or 2000? I'm not sure if any one of those equations is going to be specifically better for dark non-chromatic colors. Again, I would just go by really whether you're dealing with low gloss or high gloss colors. But I mean, these equations were all developed to improve your tolerancing. So if you're currently using Delta ECMC and it works great for you, I'd say continue using what works. If you do see some issues with it where maybe the equation is saying some things that are within tolerance when they're not visually, or vice versa, if you're having some issues with your tolerancing, then it might be time to switch to a different one and try it out. How or when should I use the fluorescence measurement in a metallic color? That's really only necessary if you're dealing with fluorescent colors. I did mention that our Spectra 2 got our single angle meter has a built-in fluorimeter for measuring fluorescence, but our Big Mac Eye, the fluorimeter is not as robust in that instrument, but it does detect fluorescence as well. So if you're using the Big Mac instrument, the multi-angle spectro for your metallic colors, it is automatically sort of taking that fluorescence into account and correcting the color numbers. Can I measure in colored plastic with your instrument or only coated parts? You should. I'm not sure exactly what you mean by in colored, but yeah, you can definitely measure plastic with both of these instruments, the Spectra 2 Guide and the Bic Mac, not just coated parts. The only issue you might run into is if you're dealing with transparent plastic. That can get a little dicey. But we can provide some recommendations for that. If you'd like to know more, please reach out to us directly. For a paint prediction database, what is the best spectrotype and delta E type to use for metallic and effect paints? I'd say for the spectrophotometer, you definitely want multi-angle. The reason multi-angle is used for effect colors is because of that flop effect that happens where the lightness changes depending on viewing angle, or even the color can change depending on viewing angle. So with effect pigments, your color can match very well at one observation angle or one measurement angle, but not at others. Sometimes if you change the observation angle, all of a sudden you see a huge difference between the two. So that's why it's necessary to measure effect colors with a multi-angle spectrophotometer. So that's certainly what you would want to choose for a paint prediction database. As far as the delta E, you would certainly want to use the DIN 6175-2, or you can pick, one of the automotive specific equations that suits you, or really the delta E Audi 2000, I'd say, would be our primary recommendation when dealing with effect colors. Okay, I see what you're saying. So the question is, if we want to match panels in a metallic silver, delta DIN 6175-2 of 2 is too much. How can I set tolerances in a specific process? So the whole idea behind the improved difference equations is to scale that delta E value so that you can use a tolerance of 1 for everything, a weighted tolerance of 1. And so that makes it simple so that all colors are able to have the same tolerance, although the way that delta E is calculated, of course, depends on where the standard is in color space. So 2 would technically, under the DIN 6175-2 equation, 2 would be out of tolerance. The higher or lower gloss affect the color lightness, or the instrument separates the gloss from the color readings? So in general, glossier surfaces look darker to the eye, darker, and for chromatic colors, they look more chromatic. Now, the difference between a sphere and a 45-0 instrument is that 45-0s measure color as we see it. So if a color is glossier and we see it as being darker, the 45-0 instrument will also measure it as being darker. And the multi-angle instruments have a directional light source like the 45-0. And so multi-angles also measure color as we see it, where the gloss is going to have an effect on the color. So the gloss will cause the instrument to measure the color as being darker for multi-angle as well as for 45-0. Okay, looks like that is all the questions we have, and I realize it is after 11, so we will go ahead and end our presentation for today. If I have not answered your question, please feel free to contact me directly. Thank you all for joining us today. I hope it was beneficial to you, and I hope you have a great rest of your day.